something I know or to some concept, or to try and understand a particular result. If I try and just digest this stuff about C components or whatever on its own terms, my eyes just glaze over.
Yeah.
So I'm curious, like when you see the C component stuff, did you think, like given your experience implementing Pyro, do you immediately think to like, oh, here's like what the analogy to that would be in Pyro, or not, or like here's an abstraction I can make around that.
Uh, no, I think you know, I guess mostly when I read these things, I think like uh, it's increase, as these graph as these definitions of types of graphs get more exotic, right? They get further and further away from a way that you would actually describe uh, a problem or describe a probability distribution as a probabilistic program. Um, so
So for me, whenever I
so
see,
the overriding question for me is less like uh, is more
oh, and
they
she,
both realistic ways of describing the uh, you know real probability distributions, and are they also since these are specifically designed to deal with um, identification and estimation in the face of model uncertainty, are they realistic models for the sorts of model uncertainty that we see in real problems? And I sort of think the answer is no on both counts.
hmm.
I mean,
um,
I think one of the challenges with relating it to real problems is that, what's a real problem looks very different for different people. And I think they're trying to be sufficiently general, but that's a big ask, right?
well, the two, so there are kind of two basic uh, um, uh, claims here, right? One is that uh, in the MAG and the PAG formalism about how one should represent an estimate for a particular problem, right? So one claim is that the
That people
form
actually work on.
know we can get kind of exact conditional independence information up to directedness, right? So we're uncertain about maybe edge direction, but not about the presence or absence of edges in a way that would upset the Markov equivalence class.
Mhm.
And the other claim is that it's easier to parameterize. It's easier to state our knowledge in the form of what ends up being a potentially quite complicated set of marginal distributions, right? Where instead of attempting to state anything about even hypotheses about uh, the mechanistic effect of unobserved confounders. And I think in biology, at least, for the problems that I look at a lot of the time, both of those assumptions are way off base. Like, first of all, there are no true zeros in biology, right? Everything interacts with everything. Like Eric Lander says, anything that can happen does.
It's
And
just
you can
small effects, you're saying.
and anything that can possibly happen does. Any interaction,
Yeah.
just about. Um, things are inherently noisy. Um, so, and then there are lots of things we can't observe, but that we have some information about, either from physical or chemical principles, or you know vague analogical intuition. Um, so, I guess that's my hot take on this paper, is that um, the as a representation, um, it falls short in those, the, the premises under which it's put forward as a representation are don't correspond to the sorts of things that strike me as important for the things that I now work on.
Wait, Eli, I just want to make sure I understand. So you're saying a PAG is not a good representation of our uncertainty in the in the conditional dependencies of a model? Maybe I just need to understand.
Yeah, I mean, what, like, uh, it's just um, yeah, the idea that we'd um, yeah, that uncertainty about edge direction. It's hard for me to like think about how I would, for example, write down a probabilistic program, a generative model where that would be you know, um, a sensible description of
Well, I mean,
uncertainty about how the model worked, and also I just don't see that in like it's because it's really quite this statement about uncertainty about edge direction, right? Especially in the examples that they give that are always sort of mostly directed or bidirected, is quite intricate, right? It's a you know a, a, a well, anyway, I just don't see that as a this
I mean,
surplus
how
form
do you,
as
so you're saying like causal discovery is just kind of not the representation you would prefer? I guess I'm just genuinely confused by, I mean, like, so the way I see it, I mean, I'll just give you my alternate view and then we can kind of see if we can resolve maybe what the differences are, right? So my view is that the hard part of causal discovery is that you can never get down to the actual DAG, right? And so the innovation here is that you don't have to. You can work with a partially specified DAG where it may be specified and it may be misspecified, but it doesn't matter as long as you know that the overall that the PAG is right, and so the details of which direction conditional independence it leaves ambiguous is unimportant as long as you can ask you if you have a causal question and you want to answer that causal question, then basically you can answer that causal question from this PAG directly without having to compile down to an individual DAG. And even if you have the DAG wrong, but it's a member of this PAG, the true model is still a member of the PAG, and even then even if you were to create a probabilistic program that based on an instance of a DAG from that class, then this algorithm would tell you which causal queries would be correct, even though you had misspecified completely some of the direction.
Yeah, that's the use case for me, which is to say,
right.
I wrote down this model, and someone comes along and says, this model, man, you don't even know if it's the right model. Like, what if it's misspecified? And I'm like, well, so long as I get so long as this model it's coming from observables in some sense, then there's a equivalence class of models that have the same properties given these observables, and here's what I can say about that entire class. And so what my model and if we have these kind of graphical representations of those classes, then they're we can and algorithms that go along with them, then we can say, all right, well then this, if you don't like my model, then just see it as a kind of I don't know, exemplar of this class, and then I can apply an algorithm to this. I can apply some algorithm to the structure of this model, and it'll tell me something about the rest of the class. So it'll tell me what I can. So it could tell me what I can know up to correct specification of the model up in terms of correct specification of an equivalence class of models, which is pretty powerful, I think.
Yeah, as long as all of the models agree on the observational distribution, then you can make causal claims that are valid for that entire class of DAGs, even though they may disagree on the details.
So I think this is useful if you've committed to a pipeline that first does, something like constraint-based structure learning and then says, given that, what do I do with it?
Yeah.
But to Eli's point, I think, if this is about an argument between two people saying, here's my model, where do they reconcile? It does seem like an awkward formalism.
Oh.
Is that a good?
Or perhaps another way of saying it is like, how is this useful beyond? I'm going to paraphrase, but I'm going to spin it in a more colloquial sense. Would say like, how is this useful beyond getting your paper past a reviewer who's hung up on this body of research? Like that might be another way of phrasing your criticism. Is that a good way of phrasing it? Like, how is this actually going to impact science?
Well,
from a probabilistic programming
I
standpoint.
don't know about that, but more like, why would you want to, why would you want to work so hard to tiptoe around avoiding writing down latent variables? Right. I mean, that's ultimately the purpose of this formalism, is to avoid ever writing a
Sure.
probability distribution over.
Yeah, that's the purpose for them, right? Like, why did they invent mags? It's like, I just want a graph that's closed under marginalization, right? But it doesn't mean that you have to use it for that reason. It can just be an ingredient to answering some query that somebody posed. Like, here's my model, and I have all my latents in there and everything. And then there's like, okay, well, can you give me some kind of robust answer to this causal question that will work even if your model has issues? And you're like, yeah, sure. And here's the algorithm. And then somewhere in this algorithm, buried way kind of three levels deep in the directory structure of your repository is a mag representation that is not surfaced to the user.
So that I buy. I guess what I would be prepared to conjecture is that there's a probably equivalent condition of about conditional independence on the DAG that includes the latent variables, right? You could probably you could probably say something of the form, given a probabilistic program that includes some latent variables, the actual model that I write down, the structural causal model that has explicit latent variables, probably there's something equivalent to there's two equivalences, right? One for the identification result, right? Whether algorithm 3 returns fail or an expression, and probably that equivalence takes the form of in your latent variable model, the intervened variables, the v complement c, v difference c in the language of this paper, are deseparated from the query variable c, right? Or rather, some subset of those whose marginal distribution you're interested in are deseparated from the observed variables in some mutilated graph. Right, and then the second equivalence would be, so this paper does two things, right? One, it tells you whether a particular distribution is identified, and two, it gives you an identifying expression if the answer is yes. And probably there's also an equivalent, relating a marginal distribution, that you just compute in the usual way on some mutilated version of your latent variable model to the
I'm writing a paper on that right now,
to the identifying expression that pops out of
Jeremy and I are writing a paper on that.
We're doing exactly. I was like, you're describing our paper.
Yeah. So I guess
It's gonna scoop us.
if my if those conjectures are true, and if that conjecture is true, and I think it is, I mean, I think it's I'm basically describing swigs again, which is why I happen to, which is why I'm such a partisan for them. Why bother with all this stuff?
Swig boy.
So maybe I underestimated the value of swigs then. So you're saying that you think the conjecture is true for swigs then?
Well, or equivalently for omega programs where the intervention is upstream of the where you're not conditioning on anything downstream of the intervention.
Yeah, I mean, I think what Eli has kind of sold me on last time we talked about swigs was that, and since then when I teach about counterfactuals, I've been kind of falling back on this logic a lot, which is that counterfactual. When I first learned kind of Pearl's abduction action inference algorithm, I'm like, okay, great, counterfactuals are done. We just have this algorithm now, and and so, but of course that forces you to kind of have a fully functional causal model, and wouldn't it be nice if there were like a class of counterfactuals that you can answer just from observational distributions? And I knew that there were some there was like counterfactual identifiability issues, but what a swig does, it just shows that like if the counterfactual is identifiable on a swig, or rather the swig gives you a whole class of counterfactuals that you don't need a functional causal model to answer. Sorry.
It's also just a recapitulation.
Grammatical. What?
Some of the it's also just kind of a restatement of some of the claims in Pearl's book about the alternative counterfactual view of causal of the due calculus and causal effect estimation, which is that the causal effects are a particular subset of this counterfactual reasoning. I mean, basically, I'm saying that algorithm 3 in this, or algorithm 1, the ID algorithm, and whatever invariant of it is in the success case is equivalent to just writing down an omega program that describes your problem, a structural causal model, and performing, doing the invention and performing inference in a useful way.
It's actually gotten me thinking, like, that conversation we had at Swigs is like, okay, well, let's see, well, if these counterfactuals that we define such that you're conditioning on something downstream of the intervention, what if Swigs kind of just form a hard line between those counterfactuals and the counterfactuals that you don't do that, and that you can possibly identify with your DAG if you have D separation in that, or with your SWIG if you have D separation in that SWIG, then great. Then what are these kind of, I don't know, downstream conditioning counterfactuals, for lack of a better word, like what are the use cases for them? And so I mean, kind of, and there you have to kind of go beyond firing squad examples and kind of think like, all right, what can I actually do with this? And so I've been kind of diving into some of
it's causal effect estimation. Anything you can do with the due calculus.
Well, you can do, but then so there's terms of kind of assigning blame, intentionality, like that's algorithmic fairness paper that Ricardo Silva put out on the counterfactual fairness. Like that definition of counterfactual fairness he puts forward is a special case of probability of necessity. And so, like, which means that if you kind of block if your DAG, if you can block the back door between the kind of protected attributes and the kind of the outcome of the algorithm that you're trying to assess fairness for, and if you can kind of import David Sontag's idea of counterfactual stability, then that's identifiable from observational data. And so, so I think there's some interesting use cases there for those I don't know, type 2 counterfactuals. Do you want to come up with a word for them? But anyway, but particularly when it comes to reasoning.
I'm against coining terms. I think that's that way lies, PAGs and MAGs and canon.
Okay, so if I can try to summarize your position, Eli, it sounds to me like if you have an SCM in hand, then there's no need for identifiability at all, because you already have what because the whole idea of identification is you don't have an SCM, you just have a DAG, and you're trying to infer what queries will be true in all SCMs that are that the causal graph is part of, right? That represent that causal graph. But if you have an SCM, then just do counterfactual inference on the SCM. You're done.
Well, the SCM I'm talking about is has latent variables in it, right? So
right. So
they, in particular, those don't correspond to any of the DAGs. The elements of the equivalence class of the Markov equivalence class would be latent projections of.
Okay. So you have So you have an SC. You have but okay. Well then,
a bigger SCM.
We should actually be specific about what we mean by latent.
Well, okay, yeah, right. Because latent is not sufficient. What we mean is not causally sufficient, causally insufficient SCMs, right?
I mean,
every SCM has latent variables.
And point is that this is something that you and I had to kind of hash out in this paper, Jeremy, but which is that when in machine learning, when we say latent, we generative machine learning, probabilistic programming, we mean that we generally mean that we have a model, generative model, where we train. When we train the parameters of the model, some of the variables in the model are not observed in the training data. Now, in causal inference, am I right? Do you disagree with that?
Yeah, I would disagree. So I would say that we're talking about causal sufficiency here, right?
No. Let's just see what we mean by latent variables when we talk about just machine learning.
Oh. Sure. Yeah, but I mean, okay. Yes, in machine learning, latent variable models are just variables that you just can't measure directly. Fine.
Yeah. So hold on. Let me finish the point. But so a hidden Markov model, the hidden nodes are the latent variables. The topic model, the topics are the latent variables. But now in causal inference, latent means that, hey, I'm trying to infer this thing that I know a priori. I want to know the causal effect of X on Y. Or the conditional causal effect of X on Y, or the this counterfactual relationship between X and Y, and I come to the table with that query predefined, and what I want is to construct an S-demand for said query. Mm-hmm. And so the first thing I need to know is if this if this thing is identifiable given latent variables, and latent here means that certain nodes in my model I don't have available to me in this effort to construct an S-demand. And the thing is that in probabilistic programming, we don't really do S-demands, right? We just have a model and we query it. And so, that's those kind of conflicting ideas of latency there. I think they lead to issues.
There are different attitudes towards latency, right? So in machine learning, latent variables are your friend. They make inference easier because they help, in some sense, to decompose the problem. But in causal inference, latent variables are your enemy, and you're trying to fight against them to get something that's unbiased.
That's another point.
But the main difference is that all SCMs have latent variables in them by definition, but the ones that are not causally sufficient are ones where the latent variables there's a latent variable associated with every endogenous variable in an SCM in its definition, but the ones that are not causally sufficient are ones where there's correlation between the latent variables, and that's where you run into problems, right? And it could be that, and that's all you need. So as long as you can, all the latent variables are independent of each other, then you're fine. As soon as you have something that's correlated, then you have problems. And
Yeah, and in fact, in
I don't
machine
think,
learning, we always pick latent variables that, by definition, induce correlation between, like, that deconnect the observed variables. Like, that's the point.
right, exactly. Like, yeah, you're actually trying to create unobserved confounders in some sense, right? And that's the whole idea of like hierarchical modeling. This is, the that's the main advantage, is that, look, I can create some latent variable that connects all that connects all of my variables, and that's an advantage, right? It induces bias, but then it makes it more generalizable.
Induces bias.
Yeah. It definitely it does induce bias. Like all of a sudden, the mean of the uh, group is no longer the. I mean, like there's a whole lecture by Richard McElrath where he shows how it induces bias. Adding latent confounders. And he doesn't call them latent confounders. He just says, adding these, higher, multi-level modeling is his big shtick, right? This is such a really useful thing because it helps generalize um, your findings, right? So you don't have to, he considers two extreme cases, right? Where you just average all the groups together and you just compute an average effect, and the other extreme where every group is its own entity and you don't share any parameters between them. But by sharing parameters between them, then you can get something that's better than either of those two extremes.
I'm actually, interestingly, working through BDA and some of these other books again, putting together.
Yeah, I got the same one right here.
Just like some multi-level modeling books. Like, we need something better than the 8 school example, which nobody.
Yeah.
Eli, is a part of your thinking, if we're being Bayesian about causal inference, do we need identification in the first place?
Yes.
Well, yeah. I mean,
Okay, let's go with this, Sam.
you at least want to know.
Actually, a guy who does talk about this, right? You don't need this. I remember his name now. Let's see if I can pull it up. And he said, so yeah, go ahead, continue with this. This is great.
Well, you at least want to know whether, if you treated your parameters as in a frequentist way, whether the joint distribution would be identified.
Yeah, I'm sort of rehashing a little Twitter discussion that
I think
came out of. Sorry?
for Bayesian causal inference, though, that, like, I mean, if you go back to our object conditioning discussion,
Yeah.
right, then typically the setting in which Bayesians are doing causal inference in the first place is in these hierarchical models where identifiability comes from exchangeability. There's not all that much work on truly Bayesian structural causal models.
Yeah, I guess let me be a little bit more precise then. So if you, let's say that you are a pure Bayesian, right? And you write down a prior over structural causal models that include variables that could be construed as latent confounders.
1 second. We're being Bayesian about the model, or being Bayesian about parameters, or both?
Let's say we're going to restrict the model class. So we put a point prior, we put a delta prior on the the family of functions. So I don't know, it's linear models or something, but we're going to be Bayesian about parameters, and therefore we're sort of implicitly being Bayesian about the structural causal model itself. So
okay, so they all have the same structure, but there's just different parameters. Is that what you're saying?
Yeah, sure. Yeah, sounds good. So let's say we write down a prior over functions, over linear functions, some of which over latent variables that confound treatment and outcome variables.
Mhm.
I mean,
Are these confounders observed or not observed?
unobserved. Yeah, latent confounders. Yeah. So I guess, so my claim, it's kind of jumping to the punchline, is like, if you really, really believe your prior, you're fine. But we're quite bad at writing priors. And the things we lean on in Bayesian inference that let us kind of step away from the priors, things like Bernstein von Mises, don't apply in settings where there's confounding. And therefore, we're much more sensitive to misspecification of the priors when it's not identified.
Mm-hmm.
So my argument is essentially like, we should care about identifiability when we're Bayesian, because then we can kind of like relax a little bit if we're wrong.
Yeah, I totally agree. And that's kind of the purpose of hierarchical modeling, right? I mean, what it tells you is that your query variables are conditionally exchangeable, and thus that it's okay to be Bayesian about your latent parameter.
The way I think about it is, I personally combined Bayesian methods with causal methods when it came to causal discovery, and this is where because that's the equivalence class was just like, oh, okay, so here's a whole class of the thing that I'm trying to infer, where everything has the exact same posterior probability, and so like they're so if they're likelihood equivalent because of the Markov property, then they are posterior equivalent, unless my prior incorporates some kind of causal information that can favor one Markov equivalent graph over another one. And so that kind of brought me towards, and so like that's where when I first encountered the PDAGs and the PAGs, because it was like, okay, so as somebody who's actually implementing an algorithm, I want to kind of reason. I also make my life a lot easier if I can if I can search over the space, if I can assign like a probability to the space of PDAGs or PAGs as opposed to the space of DAGs and MAGs. And it also got me thinking about, you've seen work from like Bernard Shokoff's circle with the information algorithmic theoretic stuff about kind of how the true causal direction will have some kind of minimum description length that's smaller than the other ones, or rather like the information will flow through it more naturally than the other ones. And I know we have that kind of thinking in probabilistic programming. Some of the kind of I don't know, and maybe like, are you guys familiar with that idea of Bayes-Occam's razor and other kinds of ideas about how information flows through a program, and how we might use that, for example, in kind of Bayesian program synthesis and induction. I'm curious if any of those ideas any of those things have you guys have had similar thoughts in that direction? I'm looking at Zena in particular, since I know he just presented a paper on that.
Yeah, I think these are all good points. To your I guess first your questions.
Can you speak closer to the mic?
Sorry, yeah. So to Sam's point, I pretty much think of this in the Bayesian sense. Let's define a prior over our models, right? And then everything kind of follows, through Bayes. It could be the case that, our prior is misspecified. And it could be the case that even with infinite infinite observational data, we can't, narrow that prior to, the true model. But this is always true in Bayesian inference, right? And so I don't really think of it any differently. One thing that is interesting that we can do in the causal world is that we can condition on interventional data. So it's like saying, I did some experiment, I got some result, and I can add that interventional data to my observation in a purely Bayesian sense. The kind of applications, like, I guess I think about it like, what is an equivalent class? It's like strictly less information than a posterior, right? It's saying all of these things are possible, right? But I'm not distinguishing between them. To your point, Robert, I think all of these criteria are, they should follow out from Bayes in some sense, right? Like, they're almost like heuristics, right? Which may be grounded or to various degrees, but you shouldn't necessarily need to impose them on top, although that may lead to more kind of practical methods in practice. I guess I'm biased. I do like to stay in Bayes land. There is obviously the big problem, which is where do your priors come from, especially in these spaces which don't necessarily have an intuitive prior. Like, what are you going to specify as your prior of a causal models? And then you go into weird questions like, does it make sense to have a data-driven prior, right? Like, somehow I want my prior to be a function of my data, and so people, some people say that's just wrong, right? Like, what does it mean for your prior? Aren't you using your data twice if you use your prior if you use your data to construct your prior, and then you condition your prior with your data? Isn't that just kind of like the devil's work? But I actually think it's
empirical
fine.
base. I mean, it's like an old argument, though, yeah.
Yeah. So, overall, I think I could be. I could be missing, a lot. I could be missing the point, but, well, actually, I think the merits of the kinds of questions in this paper, granted I didn't fully read the paper, and it's related to a lot of the stuff that we've already read, is can you make your queries robust to the things that you're not sure about, right? But then I would take a much more query-driven approach than trying to change my underlying formalism, right? And yeah, I think that's a valid thing to want to be able to say, a valid thing to want to be able to do. But again, I don't think we need to fundamentally redesign our representations to support that. Although maybe we do, I'm not sure. But I think I think we should focus on the questions that we're trying to ask and answer, rather than kind of the other way around.
Yeah.
So I think I agree with you largely. I guess one, I would say I'm more a Bayesian than I'm not, but one sort of devil's advocate question for the group is, but by claiming that we have a posterior on causal effects, are we somewhat like adding a bunch of significant figures to something we were like a high school lab report that says this concentration has 42.5937543.2%, this kind of compound. Well, the measurements you've done don't really support that level of precision, so let's not try to report it and instead say, I don't have a posterior, I just have this kind of equivalence, and if I did have a good prior and I did have a good likelihood, then I could give that to you, but I can't, so I'm not going to commit.
I suppose it depends on, how maximally Bayesian you're willing to be, right? I mean, every time you add, when you add, model uncertainty or additional latent structure, right? You're typically going to decrease the certainty in your posterior distribution over causal effects.
Mm-hmm.
Right? You're going to smear it out rather than add significant figures. You could sort of, if you were. You could take maybe there's some argument to be made that you're irreducibly biased, and that there's your secret prior that you're not willing to write down is like one part of the mass on like all the stuff you did write down, and then all the other mass on like maximum entropy nonsense. Like we know nothing about the world, and everything we say could be wrong.
Right.
Even
Right.
even this structural information that I put in could be total nonsense.
Right. I mean, there's always that sort of implicit conditioning on, you know, capital M of like conditioning on the model class that you're considering.
Maybe
I mean,
maybe a stronger
go ahead.
maybe a stronger version. My interpretation of what you're saying, Sam, is like I want my the things that I'm saying to be somewhat more robust against my subjective claims about the
Right.
world, right? And this is just kind of the fundamental issue, right, of statistics. And so I think there's an appeal to that, but it's like I think as Eli's pointing out, I think it's kind of misleading, right? We're always baking in assumptions. And so we might as well just accept that, right? And say, here are my
Yeah,
assumptions and here are my conclusions, right?
yeah, and ultimately, right, where does you know where does the epistemic certainty come from? Ultimately, it comes from mechanism, right? Like it comes from, why can we, why do we have to solve our statistics problems with this, you know, two point prior on, knowledge and nonsense, versus like, why can we, run, why can we design fighter jets with computational fluid dynamics? Well, because, we've convinced ourselves mathematically and experimentally that any query in the regime of classical computational fluid dynamics, right? Our mechanistic knowledge is completely robust to misspecification. We know classical physics. So, the robustness ultimately comes from in that case, it would appear to come from deep mechanistic knowledge about the world, and not, there's no statistical jujitsu that we can do to avoid the pitfalls of misspecification. You just have to sort of know stuff and have reasons to believe that you know stuff.
So is there
Physics is the best example of knowing stuff.
so maybe Pearl would say, you know, in our graph of fluid dynamics simulation, it's identifiable. We just haven't done the calculations yet to demonstrate it to ourselves, and that's why we can, get these robust conclusions.
Well, maybe I think he would. It would be more like even if you wrote down some. Well, I guess one thing that would make it identifiable in the particular case of physics is that there aren't actually any latent. There are no correlated latent variables. Like our simulations are deterministic and reversible. Maybe there's some independent measurement noise or something, but so in the structural causal model that you write down, you can always do, compute.
So I'm having trouble following the thread of the conversation a bit. It's more like I'm hearing certain keywords, and then I get then I think of something that I want to say that I'm not even sure is relevant to what was just said, but I'm going to say it anyway, which is that so it occurs like earlier on in the conversation we were talking about how like there's potential use case of saying, hey, I have a model and maybe it's misspecified, but don't worry, the query that I'm talking about will work for this in any other model from the same equivalence class. So this query is robust to misspecification within this equivalence class, and so we're talking about, as opposed to say structured learning, which is another problem. We're talking about now like misspecification from a Bayesian standpoint is to say Bayesians handle misspecification by being Bayesian about the model. And so there's some connection there between saying I want to be robust and saying that I want to quantify uncertainty about the correctness of my model. And so that implies that there's some kind of connection between being Bayesian about your model and equivalence classes. And that seems, and so like, for example, let's say I have a causal Bayes net. I know, according to kind of Peirlian theory, that there's some kind of ground truth structural causal model under it, but there's also an equivalence class of said models that all model the same observational intervention distribution. So that from a Bayesian standpoint, I might just say like, well, I have a uniform distribution on this entire, I'm going to put, a uniform distribution on this entire equivalence class of structural causal models, and this causal Bayes net just is the avatar of that entire prior. And so maybe, and then kind of extending to this mag and pag stuff, then, and so just kind of takes that logic and extends it to latent variables. So then the question then becomes to me, as a probabilistic programming person who can talk, because all these equivalence classes, they're only equivalent insofar as they represent the same set of independence assumptions about the observed variables. And so, or observed and latent, depending on which class you're talking about. But in probabilistic programming and programming in general, we're able to talk about properties of a model beyond just independence. We have a whole bunch of parametric stuff we can bring to the table. We have other assumptions from causality that we can bring to the table. Say, for example, I mentioned earlier exogeneity and counterfactual stability. We have some metrics of complexity, information criterion, and all that. And so, I'm very much interested in saying, okay, great, we have an equivalence class. Now, what? Now that, but this is equivalence class is a conditional dependence equivalence class. What can we, if we're being Bayesian, then how can we dive into this equivalence class and take and change it from a flat distribution to a curved one by kind of bringing other elements of knowledge that go beyond conditional independence. Anyway, that was a rant. Floored, you guys are just shocked into silence. It's awesome.
So Zena, I have a question for you.
Yeah.
Should we, if we want to commit to a Bayesian, to living in Bayes world, as you put it, should we read any papers about identifiability?
I don't know the answer to that question. I feel like somebody should tell me the answer to that question. Somebody should convince me why I should care about identifiability. There are only, as far as I could tell, there are only like 1 or 2 papers which are really taking a fully Bayesian approach to causal discovery. And there are a few tricky things that come up if you really try and do it. Like, so for example, you have to have some things remain invariant over all of the models in your class, right? If I want to be able to say, oh, I conditioned on x equals x, then that has to be a meaningful statement, right? In all of the models in my prior and posterior, right? So it's not like anything goes. Like, but again, to your question, I would just reiterate. I think my somewhat naive belief at the moment is that identifiability is kind of too high of a burden in some sense. It's almost like, being a Bayesian and saying, okay, you have to be able to infer the truth, right? Which is a bar we never set for ourselves, because we know it's never possible, right? So why should it be possible in this particular case? That said, going to the paper that you just posted, I am very much with Paul in the sense that there are things that are, Bayesianism doesn't encompass everything, right? It doesn't, the causality is real, and it isn't contained within the language of probabilities. And I do see the appeal of wanting our queries to be robust to misspecification to some degree. But I'm just saying that it's a very high burden. And you're just, it's kind of the thing where if you commit to that, you're going to shut yourself off from having some meaningful answers to some realistic questions, right?
Yeah.
So again, as somebody who hasn't read all of the identifiability papers, my somewhat naive perspective is that people have spent too much time focusing on this question rather than just accepting the uncertainty of the world.
Well, I mean, I think we don't have to. I think actually identifiability is the other way around. It's that, if you are satisfied with only being able to interpolate, probability of y given x, right? And that's your role, and you're fine with that. Then you're right. You don't need identifiability at all. It's only when you want to extrapolate, and you want to actually make decisions and perform actions in the world that you care about identifiability, right? You actually want your models to be able to help you make decisions. Then I think identifiability becomes important. But
so let me phrase the question to you then.
yeah,
Like in the real world, forget about causal graphs, probabilistic programmers.
yeah.
Do you can you name any real scenarios where you have fully identified the cause and effect, like in actual decisions that you make in your everyday life? I don't know, going to the doctor, deciding to get treatment, deciding to take a drug.
Well, I think the answer is no, but maybe identification lets you decompose that uncertainty into like something like bias and variance. We say, well, here's the causal stuff that I can never break down, right? Because I have some latent variables here. And here's the variance stuff, which is like, I don't have enough data. And maybe if it's identifiable, we can say, well, this part is pretty small, so we're going to ignore it. And then we're just in statistics land.
Well,
I phrase it
like identifiability, is just a we want to be able to infer what would happen if we did something, without necessarily having to do it, right? And so it's not, we shouldn't conflate it with the kind of conditional independence, the sort of what I would say is more like frequentist identifiability, right? That we see in all these structural causal model papers, right? Where mostly identifiability actually comes up and quite successfully in all these other formalisms, like the ones in the touched on in object conditioning, right? Where it's where maybe you have like maybe a natural experiment or that's close in some sense to an experiment that you'd actually like to do, right? Where you have like there's the very strong notion of like knowing the correct Markov equivalence class or correct causal graph, and computing and identifying expression for something from the do calculus. I think that's probably pretty rare. I think Andrew Gellman and Pearl have frequent go-arounds about this, but the kinds of identifiability that you see in identification strategies that you see in economics and the social sciences, those are absolutely real and absolutely valid, right? And often it's the only way to convince yourself that you can learn something about the world from experiments that you could never do. But often it's not quite as black and white as like there's some experiment that you can model as an atomic do intervention on a population of IID units from a known structural causal model. Exchangeability is the root of successful identification.
Zena, to get to your to answer your question about, say, exploring the world, like I think what your question kind of gets at to an interesting cultural divide, which I think is partly the reason why we're motivated to put this group together, but which is that the Jamie Robbins's and the Judea-Pearls of the world are interested in, in some kind of idea of rigorous identification of something that is true, while a big kind of thematic core of the kind of probabilistic modeling that we do is that we're looking for explanatory models of the world, and where an explanation is a concept from not from metaphysics, but rather from kind of from cognitive psychology, right? So it's about what is an explanation, what is and what is the explanandum, and how do we come up with things that explain that explanandum. And so, like, I think, if you can, for example, create an agent that can generate useful explanations that, for example, suggest interventions that would help it, that it could apply in the world to get some more information and update its explanations and get some utility, then why do you care so much about identifiability? I think, so I think, like, so in one sense, some people are trying to kind of solve ground truth, while the other people are trying to come up with useful models. And that's more Bayesian in a sense, where, because like you said, in Bayesianism, you don't really go for objective truth. You try and, if you're the best thing you do is use decision theory and try to kind of maximize some expected reward or minimize some expected cost, and make decisions that way. And so I personally, I think kind of maybe a personal mission of mine is to reconcile the two worlds. But you're right. There is a kind of fundamental gap between those two philosophies.
So I have a proposal for the group, as we're running out of time. And if I remember, Eli, one of the reasons you said you were organizing this is to get collaborations and people thinking on the same page. So I guess my proposal that I want people to sit with is that in causal inference, when we don't know, confounders, people do this stuff that they call sensitivity analysis, right? You can bound effective confounders, and historically, the research I've read on this does it in a very non-Bayesian way, right? You have like adversarial regret bounds based on user specified ratios of some terms, and it's very non-Bayesian. But all this is to say, I think us as a group could write a paper just making the case for being Bayesian about sensitivity analysis, which is really just put priors on your latent variables and see what your posterior is, as like a case for the wider research community that this is an idea to be taken seriously and fits into a task that people already do, but just think about it differently.
Mm-hmm.
Yeah, and in fact, I've seen some of those sensitivity analysis papers, and you can always kind of point to one of those methods you're talking about, and just kind of, if you take a Bayesian approach to it, then Bayes estimators are always admissible, right? So that means that any good sensitivity analysis approach you find, there's always some, assuming you use proper priors and all that, there's always some Bayesian analog to it that's admissible, right? So it'll always do at least as well as the proposed the state of the art approach. That's
yeah. I mean, I think, go ahead, Senator.
Yeah. Well, just a few quick comments. So one, Sam, I think that's a great idea. And if you point us to point me to some papers to get an in-depth understanding of the kinds of sensitivity analysis that people are doing, then that would be great. Because these aren't typically the papers that I read. I'm honest.
Yeah, totally.
To be honest. To your point, Robert, I wouldn't, so you kind of put up this axis of truth versus usefulness, and I kind of feel like I'm not quite going into just the usefulness territory. It's more like that truth is unattainable. And for me, this is in some ways the Bayesian philosophy. How do you reason when truth is unattainable? How do you reason with degrees of belief? And I just think we should take that philosophy and extend it to the to everything.
And I agree with you. Just to inject, that's what equivalence classes attracted me to. Is like, so you have all these people arguing about like, oh, we need to seek objective truth. I'm like, well, you can only get it up to an equivalence class.
Right, but an equivalence class is a set, right? And a probability distribution is a set with some more information on top of it, right? So it's just like, do you want that more information or do you not? But I think the other part, as we've said a few times, is actually sometimes you want your queries to be robust, universally quantified over that set, right? And this is, I think, one of the things that this approach is giving us. Running out of time, some entirely unrelated point is that one of my friends, Kuldeep Mill, has this new paper called, it's like on testing samplers. It basically has this way to kind of test equivalence between distributions, and he has this older paper which I think is really cool, which is basically how to sample uniformly from SAT solutions, and it's a really cool approach. And like in the last 5 years, it's been in the back of my head to how do we extend this to kind of a broader domain. And so, if anyone is interested, he wants to talk about it. He's like super excited, and he wants to tell everyone. And so, if anyone's interested to listen about that, not for this meeting, just in general, I'll probably send out an email. So let me know if you're interested.
Yep.
Yeah, I'd be interested.
Yeah, that sounds good.
Me an email. Yeah, I'd be very interested. What should we talk about for next time? I know last time, Eli, you were like, let's talk about some estimation methods that will work for they're efficient estimators, right?
Yeah, I think so. We could also do sensitivity analysis. Sam has a particular paper in mind.
Yeah, I would really like to do either something like TMLE, targeted maximum likelihood estimation, which again, from last week, I have no idea how to put that in a Bayesian setting. It's just very, very weird. Or something like sensitivity analysis would be great.
So I have a paper, and so I have kind of so in the All Deep community, I have a kind of running schedule. So for the for the 21st, and the 28th, I put that TMLE, targeted maximum likelihood for causal inference in observational studies by Megan Schuler and Sherry Rose, and then after that, targeted learning, causal inference for observational experimental data by Mark van der Laan and Sherry Rose. So I think it makes sense to, like, if we're going to hit a topic, then just kind of, have a bit of a kind of sprint on on a few papers within a field before moving on. But so I already have that kind of dot in the schedule. But if you want to do something different, we can do something different.
Well, so I just put a Carlos Sinelli paper out there for sensitivity analysis. I don't know if that's what you meant by sensitivity analysis. We should probably just put a whole bunch of sensitivity papers out there and kind of vote on them, right?
Yeah. So I haven't read that paper, but just looking at the title, it looks like the same thing.
Okay, cool.
Yeah.
So I'm very interested in going in sensitivity direction. If we're going to go in the estimation direction, I would put out as a candidate paper to read the weighted empirical risk minimization paper that Barenboim just recently published. And the advantage of that approach is that whereas TMLE and a lot of these super learners, they're good at a specific estimand, efficient estimators for a specific estimand, this method gives you an efficient estimator for any identifiable estimand.
But aren't we still, I mean, I don't know, for me, it's just like, do we as a group want to keep diving into identification and estimands, right?
Well, I would articulate my original, my original rationale for starting the group as how do we, sweep away the jargon and consolidate all these ideas in, under the Bayesian umbrella, in represented as probabilistic programs. So to the extent that any particular paper furthers that agenda, I support it. But I agree that, I'm a bit graphed out.
Right. So I think the TMLE and the estimation stuff is interesting because it's not obvious how it fits.
Yes,
sensitivity
and
analysis
that's a
stuff.
that's a great rationale for going
Yeah.
in a direction is to figure out, you know, how we can expand our, you know, our little empire of the mind.
Right. The sensitivity analysis stuff, I think, is the opposite, where I think the Bayesian way of thinking is a natural way of doing this thing that people already talk about doing. And
Yeah, there is some interesting, I guess, more graphy literature related to sensitivity analysis as well, in the form of I guess what the Perl literature tends to call Verma constraints.
right.
Give you bounds on which are sort of bounds on the marginals that correspond to, you know, whereas in sensitivity analysis you might be doing posterior inference over your you know, for your latent confounders. Verma constraints relate give you inequalities that relate marginal distributions in unidentified models with identified ones.
Right. Although I will say most of the literature all the literature I've seen gives you sensitivity analysis in terms of bounds, not in terms of posteriors.
Yeah, I don't know much about sensitivity analysis, so, but yeah, so this seems like a fruitful direction. So
I love the suggestion of Verma constraints. I've been looking at those a lot recently. So that, you know, I can certainly mention a number of papers that kind of use Verma constraints in interesting ways, both for sensitivity analysis and also for causal discovery. There was a recent paper by Pearl that bootstraps causal learning by alternately going between doing causal inference to get Verma constraints and then using the Verma constraints as additional constraints in your causal discovery. And so it's like a bootstrapping approach. So that would be something that would be fun to look at. Or maybe some more basic papers that explain really what Verma constraints are, and making sure we all kind of like have a good grounding in that.
If you could find some of those papers and stick them in, so in Jeremy, in the All Deep community page, there's a link to a Google Doc where we're kind of having a backlog of papers. If you can stick them in there. I want to caution, like those ID papers from like the 90s and the thousands, like they suck, like to read. Like if so, like if you could find something that's maybe
more recent.
You know, recency doesn't mean that it's easier to read, but rather just you know, more. There's a little bit more emphasis on pedagogy as opposed to, you know, being as obtuse in their language as possible.
one candidate for that might be a textbook chapter, like from this.
And that's especially Verma constraints. Verma constraints is, I mean, finding, you know, those 2 or 3 ID papers from like Tien and Pearl back in the day.
Yeah, I think chapter 9 of this textbook, Elements of Causal Inference by Peters and Schultz, has a nice little exposition.
Yes, Verma
I'm gonna bounce off.
Yeah, me too. Actually,
I'll just add. Let's make sure the papers are exciting and fun to read, so we want to come every week.
Yeah.
We're gonna get some attrition if we're not careful.
Kind of
as much as possible.
Anyway, all right, so actually there's some software that allows you to do Verma constraints. That's always the easiest way for me to learn is if I have code that can give me some intuitions by playing with it, right?
Wait, like Causal Fusion?
No, Causal Fusion doesn't make the source code available. This is in Causal Effect. It's R, which sucks, but the
R is great. I like R.
But it's but Causal Effect is an R package that allows you to calculate the Verma constraints for any DAG, with latent variables.
Cool.
I have to run as well.
Yeah, I should go as well.
Jumping off.